First of all, I would like to thank the organizers for inviting me. It's a great place. I want to describe some modest recent contributions towards understanding the complexity of this Ising partition function. So first I will quickly go through background, then I will mention the additive determinantal complexity, and then some newer things, which is matching parity, and then I will, so these are kind of, let's say, negative, towards negative feelings, and then product formulas, which perhaps are somehow more towards a positive, something what can be eventually done. Okay, so background, well, graph is just a pair of vertices. Here is a graph, an example. Actually, I can probably, right? So an edge cut is given, so I will speak about edge cuts most of the talks. It's set of, so edge cut is a set of edges. Which set of edges? So that there is a set of vertices, so that this E prime is set of edges going out. So for instance, from this set V prime, 1, 2, and 3 go out. That's an example of edge cut. And the problem to max cut problem is given a graph, find edge cut with maximum number of edges is an NP-complete problem. And well, so it's even the weighted version is also hard. There is a simple version actually is when all weights are non-positive, because then it's min cut and it's polynomial. Then I will speak about even sets. So a set of edges is even if all degrees are even. So here are all even sets of this graph. So it's empty set is even, and then these two triangles and the square is also even. The degree is here, degree 3. And then I will speak about perfect matchings. Perfect matching, well, everybody, that was every day, many times here, so everybody knows. And I will speak about, well, is enumeration, so I will speak a lot about generating functions. So in a generating function, so I will associate variable to each edge, and generating function of cuts is just this multi-variable polynomial. But typically we substitute for variables. So if there is a weight on edges, then you just replace variable xi by y to weight of the hi. So then you will get a function in one variable y. So if q is a set of integers, then you will have a Laurent polynomial. Typical. And well, I will not explain it here, but this function, this generating function of edge cuts, is equivalent to Ising partition function. So I will really, when speaking about Ising partition function, I will speak about this generating function of edge cuts of a graph. And then there is this generating function of edge cuts is equivalent to generating function of even sets of the same graph, where this is the definition is the same as generating function of edge cut, and this is via McWilliams theorem, or for special case of for actually it's also the van der Waerden theorem, which we heard in the Professor Valiant talk. So, and that I will not explain. It will not be needed during the talk. Okay. So what about the complexity? So now we introduce some objects. They basically, all of them can be counted in polynomial time for planar graphs. Is this which was here? Well, this workshop is a main topic of this, the starting point of a lot of research. So let me briefly say how to do it. Well, if you have, so let's say how to find max cut, maximum even set, and maximum perfect matching when there are weights on edges, and well, how to do max cut. You make geometric duality, then by duality the cuts become even sets, so you want a maximum even set in the geometric dual, then that you transform by Fisher's construction into maximum weighted perfect matching, and that you solve by Edmond's polynomial algorithm. Okay. So this will be here later. So there is acute bijection between if you have a graph H, then you can replace each vertex by paths of triangles, and then the set of even sets here is in natural bijection with the set of perfect matchings in this graph. Okay. So that's it. And then also there is for planar graphs one can calculate the generating functions when the weights are bounded by a polynomial in the size of the graph, and by exactly the same program, because the generating function of perfect matchings is a Pfaffian. That's the Castellane theorem. And so you can also calculate the generating function of edge cuts, of even sets, and of perfect matchings. Okay, so that's background. Well, it's so for planar graphs things are all right, but it's it gets more complicated for surfaces. So there is. So assume a graph is embedded in a surface of genus G. It's just a sphere with G handles. Then so torus. Torus is genus 1. That's pneumatica. It's genus 1. So then there is a formula which is now known as Arf invariant formula. And it was basically set by Castellane, then proved independently by me and Anna Galuccio and Tesler. And then years after, Simassoni and Reshetipin gave a correct understanding of it. It is, and well, as written is wrong actually, here there are signs. So the formula is this PG. Sum, and here is plus minus I goes from 4 to the G, and this is Pfaffian. Yeah. So this is the right formula. So there are 4 to the G orientations, and they correspond to quadratic forms on the surface, and this plus minus is related to Arf invariant of that quadratic form. And well, this is Arf invariant formula is beautiful. It's and it gives and the talk somehow is motivated by it, or at least the negative part. So for fixed genus, so for fixed surface, this gives a weakly polynomial algorithm to calculate the partition functions. Okay. So so that's good, but not very practical, because it is let's say the algorithm. Well, it actually was used in calculations in statistical physics. But there are, I think, one or two physical review letters recently based on the algorithm, based on the implementation of it. But there is well, you need to, the algorithm is hard. You need to calculate, so to find the orientations is simple. But then you have to calculate Pfaffians, which like determinants, but with variables inside. So that's, you do it by interpolation. You must do many calculations. So it is hard. But there is, okay, but let's say you, at least if you are interested in enumeration, you get the whole answer. But assume that you are interested only in value of max cut. Let's say for toroidal square grid, where the weights are 0 plus or minus 1, you want max cut. There is no other known at present polynomial algorithm which would do it aside of this crazy enumeration. So that's somehow the motivation for this, for the research and for the first part of the talk is to understand this phenomena. So there is, so for enumeration side, there is an indication that actually the Arfo invariant formula is optimum. And it is a result which I obtained with mass-bound some years ago. It's, so it appeared in 2011. And it says that in a very restricted but natural setting, the minimum number of Pfaffians needed to express, I always make sorry, to express the generating function of even sets is 4 to the g. Okay, so the restrictive setting is that you somehow the Pfaffians are not of general matrices but of matrices corresponding to orientations of the graph. All right, but you can make arbitrary linear combinations. What let's say the theorem says that you cannot do it in smaller number than 4 to the g, where g is genus of the graph. Okay, so it, for instance, it gives an enumerative characterization of genus of the graph. Okay, if enemy gives me a graph, if if I can, I find the minimum number of Pfaffians so that the generating function of even sets can be expressed as linear combination, and that is 4 to the g, that minimum number is 4 to the g, where g is genus of the graph. Okay. So that is, so it's an indication that for this enumeration, Arf invariant formula is perhaps optimum. Okay. So it's, for instance, it's important here that it's a generating function of even sets. Okay. It's not, for instance, it's not known that you need exponential number if here E is replaced by perfect matchings. Okay. It's an open problem. So if and why we were able to, well, it's the proof is not, well, it's involved a little bit, and it's crucially uses that even sets form a binary linear code. So there is a linear algebraic structure involved. That's a crucial ingredient here. And as I said, for the same thing for perfect matchings, it's conjectured, but nobody can show that it's exponential, that one needs exponential number for perfect matchings. And it's not, actually there are examples for perfect matchings that it's not power of 4. There are examples that the minimum number is 6. So it's more complicated. So then let's say that's at least an indication that for enumeration, this Arf invariant is maybe optimum. But how about maximization? So as I said, there is basically nothing. So for maximization, you get this Arf invariant give formula of type 2 to the g times polynomial in the size of the graph, right? And that's can one do better? So that's some, or perhaps to express this as dimensionality frustration, which is a different dimensionality than in the talk of Professor Valiant, is the here dimensionality means genus. Could it be that even the simplest embedded max cut has its complexity given by the Arf invariant formula? So it's somehow extreme, negative view, right? So what is kind of simplest embedded max cut? Well, it is that, let's say, there are no weights. Let's forget the weights. And the genus is just number of crossings. Okay, so like this. So here, let's say there is K33, it has genus 1, and it's drawn as with one crossing. There are many other drawings of K33 with one crossing. Okay, so this problem actually playing with it, I somehow introduce the following problem, which here it is. I call it matching parity or parity matching, and it is designed to pinpoint the complexity of this only locally non-planar max cut. It's so you are given a graph, and now you have I don't know how to do it without weights, but the weights are modest, only 0 plus 1 minus 1 and some k, and then in addition you are given k pairs of edges. And you are given G pairs of edges, all right? And you say that matching is good if it has even a number of edges from each pair, okay? So it means 0 or 2. So you can think of it that you have somehow the pairs. You have a graph where vertices are are edges, and you have this. Edges are the pairs, so are some auxiliary graph, and you want perfect matching so that this, so that these vertices are covered. I say it only if you know this matroid parity problem. So that's in the setting of the matroid parity, formulation in that setting. And the question is there a good perfect matching of weight at least k? That is the problem. Right? And there is a simple algorithm to solve it of complexity 2 to the g cut times polynomial of n. Because you just guess, you just take any set of those pairs, you delete the vertices. If they don't form matching, just throw that case. If they form a matching, delete the edges, delete the vertices of these guys, and then delete the remaining pairs and make maximum weight perfect matching in the rest, right? And then compare the result, take the best. So that is the kind of straightforward algorithm. We just this complexity, and well, I can show that this max cut with G crossings can be reduced to the parity matching with 2 G pairs of edges. So, and that is somehow, I will not, so one needs to work a little bit, it uses geometric duality, but it's not so surprising, because, well, look, we are interested in, if we, let's say, take toroidal square grid, and we are interested in edge cuts. Then in the, what are the geometric duals of edge cuts? Well, they are even sets, but not ever in the dual, but not every even set is a dual of edge cut, right? They must be contractible, somehow, the even set. So how, and in, well, how to say this contractibility, contractibility in this, in the sense of, let's say, toroidal square grid, it's replaced by parity conditions. So you want even sets which, let's say, from this set of edges it has even number of edges, and from this set of edges it has even number of edges. So somehow using geometric duality on surfaces of genus bigger than 0, the edge cards are turned into even sets with parity conditions. Okay, and so then well, it's just an indication where the parity comes. It comes from geometric duality on surfaces of higher genus. And well, this, let's say, the frustration view of this max cut, embedded max cut, leads to the conjecture that there is simply no better algorithm that algorithm with its complexity 2 to the g. So for this, so the conjecture is that if I consider this parity matching, I cannot have better algorithm than of complexity 2 to the g. Okay. So so it's extremely strong, the conjecture. It somehow says that if somehow that if even in the simplest embedded setting, namely that genus equals the crossing number, the best, if I want to max cut, the best I can do is use Arf invariant formula. I cannot do better. So it's somehow it should be wrong, right? But perhaps not. So I tried to, so let me explain an approach which likely doesn't lead to a contradiction with the conjecture. And it's, so here is a standard way to look at matching problems. It is that basically you make the matching the generating function of perfect matchings, make of some you are given a graph where you have a crazy matching problem like exact matching or this parity matching. What you do, you construct a new graph, G prime, make some substitutions for edges, so to have some more variables than one, make a generating function of perfect matchings, and do it so that so that's a multivariable Laurent polynomial, let's say, and so let's say you should do it in such a way that your problem, the answer to your problem is yes, if and only if some coefficient of this generating function is non-zero. Some particular coefficient is non-zero, okay? And that actually, so this problem, let's say this coefficient problem, there is a randomized algorithm to do it based on isolation lemma. So you can do it by calculating a Pfaffian. So that is kind of standard way to do this matching problem. Let me do it concretely for this case, okay? So this a bit technical. So you are given the graph and you have G pairs, and then let's say, so this coding would be by a non-negative integer matrix that somehow will, the matrix will code the substitutions, and then what you do, to each edge you associate a monomial, basically to you for product of, so if you have G pairs, so you have G columns, and then if for the first edge you put Yj to Aj, and for the second edge you take inverse, right? And then you make the substitution. Here again, it's basically. Here you of course there somewhere need to be the weight, the original weight, so there actually here should be xe, ye, z to the we. Okay? And then now you want to say that there is a parity matching of size at least k if and only if there is some k prime bigger or equal to k, such that the coefficient of this guy to z to the k prime times 1 is non-zero in the new polynomial. And this here, you use crucially... není to vidět. Well, it was not visible. Okay. So, well, if you use both of or none of pairs, clearly you get each of these auxiliary variables to 0, right? But then there are many other terms in this perfect matching, so they in fact could have all zeros, but there you use the metric, use the property of the matrix that it has no non-trivial 0, 1, -1 vector in the kernel, right? So if you have a matrix with this property, then it's true. Okay, but well, and then still you have this hard problem to say whether a specific coefficient is non-zero, but there is isolation lemma to do it. So so then you do it by calculating Pfaffian. So you put some random weights, blah blah, and make Pfaffian, and that will then you look at the coefficient in the Pfaffian. And if in the Pfaffian the coefficient is non-zero, you say yes, otherwise you say no. Okay. So then really the complexity of this boils down to calculate the Pfaffian. But now the Pfaffian, well, it's polynomial, it's a determinant type expression, but here it has variables inside, right? So really the complexity of it depends on the number of variables and their degrees, right? And they are given somehow by this matrix. And it turns out that this property requires that actually the natural somehow lower bound for the complexity of calculating of this Pfaffian is exactly 2 to the g. Okay, so if you, let's say I took it as if you want to do it by interpolation, so then this is a natural number of substitutions you need, and that is unfortunate. It is at least 2 to the g. Okay, so this is a root indication that perhaps using this coefficient problem and isolation lemma will not give you a better way. So, but maybe there is other way, or maybe you can use it, this isolation lemma, in more clever way to avoid these matrices. So, anyway, that's the problem. So, actually, how much time do I have?
15 minutes.
Perfect. So then there is. So this was the negative part of the talk. And now let me try to say at least something.
So the parity matching problem for planar graphs. So what's the?
I don't know. Oh, but no, it is. I did not think about it. It's somehow it should be. It's a good question. But I don't know offhand. I would think it should be doable, but I don't know really. Okay, so here I want to. Okay, so. It will not be about, let's say, efficiency of calculations, but more about presenting this generating function of h-cuts in some way from which perhaps we can deduce some new information about the Ising model. And it is basically the goal here is to write this generating function of even sets, or this Ising partition function, as a product. Okay? And that's why it's an important product formulation, because then perhaps you can study logarithm of it. And perhaps perhaps that could lead to some new insight. Okay? So first of all, so this is a classical approach. First, I think it was suggested by Feynman in the beginning of 60s, and it is that it is that the square of this even sets partition function can be written as a product over a periodic closed walks of this thing, where -1 is to rotation of the closed walk. So that is for planar graph. So imagine that the graph is not only planar but embedded in the plane, so that each closed walk has somehow rotation, and then you have this formula. And it is it's formal product. This set is infinite for it's not infinite only for trivial graphs, and the formal product is just a formal power series. You look at it in this way. So it is the equality is on the level of formal power series. So the coefficients are equal. Okay. It's a basic formula in statistical physics. Then there is, so it's for planar, and it's somehow, this formula is runs in parallel with Pfaffian orientation. So this again, if there is an Arf invariant formula for general graphs. So if you have a graph of genus G, and this Ising partition function is linear combination of square roots of such infinite products. Okay, so all right. So then a natural question is whether, so that of course is somehow hard to make a logarithm. So a natural question is, can this EGX, G general, be written as a single product? Okay. So that's what we did. Let me say, but it's somehow, we don't know how to generalize the Feynman infinite product, but it turns out that it's natural to generalize another way how to express the generating function of even sets as infinite product, and it is using Pfaffian orientations. Okay, so there is always this interplay. So for some somehow in there is some conjectured relation of this Ising partition functions with quantum field theory of free fermions, and there seems to be this Feynman product, since it has rotations, complex numbers, that seems to be successful. But so here there are it's more successful, this Pfaffian world, at least for us. Maybe actually our way is not the right one, but let me explain. So what you do? You have E. You have E. You make from it a generating function of perfect matchings using this Fisher construction, right? It's planar. So it's Pfaffian, all right? So it is, so square of Pfaffian, square of this Pfaffian, which is square of this E, is a determinant. But then this matrix naturally write as identity plus some other matrix by reordering indexes of rows and columns, and then use Bus theorem. Okay. So what is Bus theorem? Bus formula. So it is exactly a way to express determinant of I minus AD, where A is a matrix, as an infinite product, in fact, as something called discrete Ihara-Zellberg function. That discrete Ihara-Zellberg function. So, well, let me just say it. So if you have, so it's a way to look at a matrix is that there is a digraph associated with it. Well, and so let me do it So in fact, every matrix can be looked at in this way, but let me go the other way. If you have a directed graph with no loops and weights on arcs, then discrete Ihara-Zellberg function is product over a periodic closed walks of 1 minus the entries in the matrix corresponding to edges of the walk. So if the entries are typically for us it would be x to the weight of the arc, then it would be product of x to the weight of a is in an arc of the walk. So it's even again infinite product, and Bass proved that the determinant of I minus AD is equal to this function. It's expansion of determinant as infinite product. So this, it turns out that this is the two-dimensional setting which we can generalize. And it's actually a long program which I started with a student 3 years. It's about it's about writing weight enumerator of general linear code, binary linear code, as to study that. So the idea is this. So even sets, it's cycle space of the graph, right? And then so it's binary linear code, which is, you can look at the graph as a geometric representation of the linear code. And it is advantageous because, for instance, you can draw graph on surfaces and use Arf invariant formula. Or if you are lucky, the graph is planar, you just, okay. So it's a useful representation. So a natural question is whether general binary linear codes have geometric representations. Okay. And I want to represent not the code itself, but its weight enumerator. And it turns out that it's actually in a theorem of Ritchie, which appeared recently, that it can be done for a linear code over prime fields. And in fact, if P is not prime, then it cannot be done. There is somehow, it's technical, I will not, it fails kind of miserably. So for prime fields, there is and you can do it by a system of triangles. So to represent, so for cycle spaces of graphs, you need one-dimensional simplicial complexes. But, and for general, you need two-dimensional simply. You don't need to go to higher dimension. It's enough to have system of triangles. Yeah. And it's actually not only for p equal to 2, but for any prime. And and so you have that the weight enumerator of your code is easily computable from the weight enumerator of the cycle space of the system of triangles. So then this simplicial complexes is somehow easiest to understand in terms of hypergraphs. So here is, and that leads to consider, instead of graphs, hypergraphs, and then somehow naturally you will not have determinants and permanents, but hyperdeterminants. Okay? So here is kind of setting. So if you have, so we say that something is k hypergraph if in each edge has size k. Graphs are 2 hypergraphs. They are almost disjoint if each pair of edges intersect in and move one vertex. It's k-partite if there are k layers and each hyper edge intersect each layer exactly once. And it is directed if the edges are ordered. Okay, so that's like for directed graphs, the orientation of an edge means that the edge is directed. right? So you say what the first element, second element. So similarly here it's the directed, you take linear order of each guy. And then you define similarly for directed graphs, you define the adjacency hypermatrix. It will be of size k, which somehow is defined in the same setting as for directed graphs, where here A is just the directed edge. And then there is, well, basically one ingredient into this product representation is the following theorem. It says that if you have a binary linear code with some weight, then one can construct a directed 4 hypergraphs D and the weight function so that the weight enumerator of this C is the 4-dimensional determinant of this form. So this identity plus ADZ. Okay. So, well, there is, okay, so this is determinant, but is 4-dimensional determinant, so computationally it's hopeless. It's hard to calculate hyperdeterminants. Well, it's easy to calculate determinants for 2 determinants, but higher than 2 is hard. Okay, and well, it is somehow, and this proof of this theorem really follows this Pfaffian theory. So it uses, you take the representation by triangles, which somehow gives you a construction of 3 hypergraph. Then there is this Fisher construction, which replace this set of triangles. That also it can be done. So you replace by this cycle space by set of perfect matchings, and then this set of this generating function of perfect matchings, it can be turned into this somehow generating set of perfect matchings of k-partite hypergraph, which is permanent of this this 3 hypergraph. And then these 3 permanents can be turned into 4 determinants. And that in general, let's say, 2 permanents can be permanents of general matrices can be expressed as 3 determinants, and in general k permanents can be expressed using k plus 1 determinants, and that's using Pfaffian orientations. So let me just maybe quickly say that. It's maybe 2 minutes or how? No, okay. Is it how it's? Is it, or are you already was supposed to finish?
Well, it's not over time, but that's fine. 2 minutes, I mean, we should survive.
Sorry, okay. So this, anyway, so if you have k-partite hypergraph, it's matrix, you want to calculate permanent, and so it turns out, it turns out that if there are k-1 by naturally associated k-1 bipartite graphs, and if each of them is Pfaffian, for instance, if each of them is planar, then the whole matrix is Pfaffian. So it's a weak condition which needs to be satisfied. All right, and so it means that it's much more hyper matrices which are Pfaffian for k bigger than 2, and that somehow is used. Okay, and the last ingredient is this 4-dimensional bus theorem, which I proved. Thank you for your attention.
Questions? Comments?
Could you go back to slide 7, I think it was?
I will try.
Okay. I think you also said that this was the only known way to calculate this. Did that apply to this as well, or was that just for...
For general, as far as I know, there is let's say, concretely, let's say, if max cut in a toroidal square grid, weights 0 plus 1 minus 1. I don't know a combinatorial way to calculate it. The only way I know is that you'd make the whole generating function and look at the maximum exponent.
There is a paper by Bravyi on contracting matchgate networks, non-planar matchgate networks. It's still 2 to the 2g time, but it's a very different approach. It doesn't rely on doing...
Oh, I would be very much interested in it. You did not know about. So, and that, yeah, it doesn't do enumeration.
It's locally, yeah, that's the right answer.
Yeah, so it's anyway. I'm very much interested in it. But let's say this is really extremely simple combinatorial setting, right? So maybe there is somehow go 10 steps here, 5 steps up would work, but I don't know. I don't know it.
The running time also involves a polynomial in M, which is the number of edges you have to remove to make it planar. So it's a bit weird that way. But I'll show you.
Thank you. I'm interested in it.
It's not because